Hello, everybody, and welcome to the Astro Show, the place to be if you're curious about the cosmos. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brain of astrophysicists, get advice from a space doctor, find out what astronomers have to say about life, and learn about what's happening up above your head, all in the same place. You can join us every other Tuesday, now on the second and fourth Tuesdays of each month at 6 p.m. Mountain Time on Twitch, YouTube, and now Facebook as well. You can chat your questions on Twitch and YouTube, and you can also call in and speak to us live, which we would love for you to do. And the information to do that should be visible on your screen. You can call into our Zoom link and ask your questions, or just make comments and joke along with us throughout the show. We'd love to hear from you. In this week's show, we have Dr. Steve Lawrence, professor of physics and astronomy at Hofstra University. He studies light echoes from exploding stars, and he will tell us all about them later on tonight. But before we bring Professor Lawrence on, let's introduce our co-stars. First, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hi, everybody. Good to be here.
Hey, Danny. Next, Director of Education and Public Outreach at Vera Rubin Observatory, it's Dr. Lauren Corlees.
Hi, good to see everyone.
Hey, Lauren. Next, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. And last, but certainly not least, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy, it's Nora Bailey.
Hey, everyone.
Hey,
Hopefully
Nora.
this is the last week.
Woo-hoo!
I am not the only non-doctor.
Oh, you're a doctor in our eyes, Nora. But we're glad to hear that it's going to be official soon. All right, folks. Well, we are going to dive right into astro advice. And we're going to stick with the theme that we started last time with adding some trivia in. And so we're going to give you a quotation. And we're going to give you 4 different possible quoters. And we're going to ask you to cast a vote, each of you 4 co-stars, for who the correct quoter is. And no checking on Google or any other search engine. That doesn't count, even though we're virtual here. So here is the quote. If you want to know, you ask a question. There's no such thing as a dumb question. It's dumb if you don't ask. Very nice. So your 4 possibilities for who actually said that are A, Sally Ride, the first American woman in space and 3rd woman in space overall. B, Katherine Johnson, preeminent NASA mathematician. C, Marie Curie, Nobel Prize winning chemist and physicist. And D, Mae Jemison, first Black woman to travel in space. So we'll just we'll go around the horn here, determined by where I see you on my Zoom window. So let's see, Lauren, you are up first. Lauren, who do you think said that?
Not entirely certain. I think I'm going to guess Katherine Johnson. I feel like
Okay, so
being
we
able
got-
to ask questions. Yeah.
Very nice. Okay, so we got 1 vote for Katherine Johnson from Lauren. Danny, you're up next.
I'm going to go with Mae Jemison.
Okay, 1 vote for Mae Jemison. Nick?
Keep it interesting. Go Sally Ride.
Okay. 1 vote for A, Sally Ride. And last but not least, Nora.
Recording in progress. Recording stopped.
Yeah, I actually was thinking C. So as crazy as that is, I guess we're covering it all here.
Okay, great. And we're going to go 1 vote for Marie Curie. And the correct answer, next slide, please, is Catherine Johnson. So 1 point for Lauren. Nicely done, Lauren. And of course, Catherine Johnson was recently immortalized in the film Hidden Figures. She was one of those incredible women mathematicians at the time known as computers at NASA. This was back so long ago in the 60s when women weren't allowed to be professional astronomers at NASA. She also had a huge hurdle in the fact that she was Black, but is regarded as probably one of the most brilliant mathematicians that NASA's ever seen. She was responsible for doing much of the orbital mathematics for the first human space flights. Alan Shepard's space flight, John Glenn's space flight. She did all the math to figure out how those orbital trajectories were going to work out. So thank you, Catherine Johnson. And yeah, and a fabulous quotation as well. So if any of the co-stars have any thoughts about the quotation, we can chat about that for a few minutes before we move on.
I really like this one. It's hard because especially when you're new and you're trying to do something and learning, when you have some of the most important questions to be asking, you definitely feel like, oh, I can't say anything. I should know this. What do people think I'm dumb? And so just learning how to like break out and say, no, I'm going to ask my question. I'm going to take up the space. I'm going to ask the question and I'm going to get the answer that I need. It's hard to do, but once you start, you realize that it's actually not as scary as you think it's going to be. So.
Yeah, I think I remember hearing from multiple teachers over the years that if you have a question, there's probably 10 other people in the room that have the same question.
Yeah.
Nora, are you going to say something, or Danny?
That's what I was going to say.
Yeah. I didn't mean to steal your thunder. But that, I mean, that's the truth is, we typically have a lot of the same curiosities. So asking them doesn't always just help us out. It helps everybody else out as well.
I think I really like the first part of this where it says, if you want to know, you ask a question. And I think, I'm trying to think of the right way to say this. I get a lot of questions. I do a lot of science communication work and I get a lot of really amazing questions and I love answering them. And I don't think there's any question that's too dumb or too basic or anything. But I do get questions that people don't actually want to know. They're asking the question because they think it's a gotcha, or they think they're going to trap you into saying something, or it's just an excuse for them to tell you how you're wrong. And that is very frustrating. So if you actually want to know, please ask questions. But if you don't, then maybe consider your options.
Yeah, so true. So true. Anything else? All right. Let's move along then to Astro 365. So today in 1802, having a little feedback here. Hopefully no one listening in is hearing that as well. Try that again. So on this day in 1802, Heinrich Wilhelm Matthias Olbers discovered the second astronaut, Pallas. That was just 1 year after the very first asteroid was discovered, Ceres. It turns out that Olbers also discovered Vesta shortly thereafter, and discovered another asteroid, name of which I can't remember right now, but as of the early 1800s, he was responsible for finding 2 of the 4 known asteroids. You may also recognize his last name because of a very famous paradox in astronomy known as Olber's paradox. It turns out that he was not actually the first one to come up with this paradox, nor was he the most prominent astronomer to actually come up with this paradox. It sounds as if Johannes Kepler mentioned something very, very similar. as did Sir Isaac Newton and other notable astronomers. But for some quirk of history, we now know it as Olber's paradox. And if we go to the next slide, it has a nice little demonstration of what Olber's paradox suggests. So Olber's asked a really basic question, which is, why is the night sky dark? At the time, it was unknown whether the universe was infinite or finite, but astronomers postulated if the universe was indeed infinite and there were an infinite number of stars, then shouldn't that light be streaming through space and eventually fill up the sky with starlight so that it was bright as the sun during the day? It seemed like a reasonable conjecture, but clearly the sky is not like that at night. It's quite dark, even with the glimmering stars we get to see in most locations. So if we can advance the slide, we can see a little GIF image of what that looks like. Maybe we're having a little problem with our slides. Oh, there we go. All right, so yeah, now that GIF image is working. So this is a demonstration of if there were an infinite number of stars in the universe all streaming towards the Earth with their light, eventually that starlight should fill up the nighttime sky, but it doesn't. And it took until the 20th century for us to have actually direct evidence to understand Olber's paradox. But interestingly enough, the first person who actually postulated the correct answer to Olber's paradox was not an astronomer at all. It was actually Edward Allan Poe, just a few years after Olber's first asked this question in the early 1800s. Edward Allan Poe postulated that perhaps stars are just so distant that their light hasn't actually had time to reach us yet. And today we actually know that is part of the answer. The universe also happens to be a finite age, and it also happens to be expanding and actually accelerating in its expansion. So as the universe expands, things are getting farther and farther away from us. Their light also gets stretched out into wavelengths outside of the visible range, so we can't see that light visibly anyways. And so we now know that that is the correct answer to Olber's paradox. But yeah, Edward Allan Poe actually got it about a century before astronomers knew the answer. So nice work, Edward. All right, so now on to the other portion of Astro 65, our Astro News quiz. We're going to switch up the order this time. So we're going to start with you this time, Nick. So I hope you're ready for this. I'm going to start you off easy, and the questions are going to get harder and harder as we go.
How exciting.
You ready? All right, here we go. Tomorrow, NASA plans on announcing a new discovery that extends our understanding of the universe and creates an exciting area of research. A discovery made from which old telescope?
NASA, it's probably something in space. Let's just go with Hubble. Hubble's a classic, you know.
Yeah, you got it. Nicely done. All right, 1 point for you, Nick.
Goody.
Yeah. Okay, number 2, X-ray jets from pulsars.
Always the jets.
Oh, always the jets. X-ray jets from pulsars are now believed to be the source of this type of matter found on Earth.
X-ray, gold. Why not?
Nope, not gold. One more guess for you. It's a little more esoteric than gold.
More esoteric. All right, denser, lighter. Where are we going with that?
Think much smaller. Much smaller.
Ooh, smaller.
We're going yeah.
But it's on Earth.
Subatomic here.
Subatomic on Earth.
Mm-hmm. Was detected on Earth.
Detected on Earth. Okay. Yeah. We do neutrinos? We doing some neutrinos?
So close. It's positrons, antimatter.
Positrons.
Sorry, I can't give you that one, Nick. All right, third one.
Darn.
It's okay. The interiors of protons were recently experimentally shown to have the maximum amount of this. Interiors of protons were recently experimentally shown to have the maximum amount of this.
One of the forces.
You're on the right track. It's not a force, but something something related to that level of existence. What was that?
Get into my particle physics, which I probably should know.
Dive into that. Dive in deep.
What could protons have? Okay, so
Maximum amount of this.
quirkiness.
Oh, you're so close. It's quantum entanglement. Maximum amount of quantum entanglement. Yeah. Okay.
I mean, that's probably what quirkiness is.
We can give you that one. Okay. We're sticking small here. The latest constraint on the mass of these particles is less than 0.8 electron volts.
0.8 electron volts. I think
you already said this for one of your previous answers, actually.
Oh, neutrinos now?
Yeah, there you go. Nicely done.
I was like, we're trying to constrain that. And I'm like, what is the constraint we have?
Yeah, 0.8 electron volts is the new constraint.
Right.
Yeah, as of just a few months ago. Yeah, but just announced last week. Okay, fifth question.
Ooh, yeah, but which experiment? Who's our competitors?
Yeah, that's a great question. Researchers at the Center for Astrophysics and the Massachusetts Institute of Technology and the Max Planck Institute for Astrophysics have created a simulation called Thesion, named after the Etruscan god for dawn. And the simulation is for what period of the universe? So it's named
dawn.
Thesion, the Etruscan god of the dawn.
But is that an acronym?
Nope. That's
sure.
Yeah, it's Thesan is the Etruscan god of the dawn, and it was named because that this model is for this specific period of the universe.
We'll go with cosmic reionization. That's
yeah, nicely done. Cosmic reionization, nicely job. So I think Nick got 3 correct answers there. Nice job, Nick. All right, we're going on to Nora now. Ready for this, Nora?
All right.
Okay, here we go. All right, last week, astronomers at JPL confirmed the discovery of the 5,000th of these.
Exoplanet.
Nice. Nicely done. Right in your wheelhouse there.
Yep.
All right, number 2. Blue Origins will not be taking comedian Pete Davidson into space later this month, but instead, they will be taking their own chief architect of Blue Origin's New Shepard's vehicle named...
I read this and I knew that it was an internal person, but I don't remember their name. It's not one that stuck in my mind.
Right.
Like Leah something, I don't know.
No, Gary...
sitting over there knowing his name and about 5 others.
Yeah.
Gary Lay was his name. Gary Lay is his name.
Oh, see, I think that's where I was thinking Leah.
Gary Lay. Yeah, there he is down there. Yeah.
Yep, that's close.
Okay, we can't give you that one. Sorry. Okay, moving on. Number 3, announced last week the first orbital test flight of Starship. This company's huge rocket will take place in the next 2 months.
Wait, what was the question? Oh, what the company is? SpaceX.
Yeah, there you go. Okay. Here's a trickier one for you. This new video game by Dutch developer Kyoken Interactive, available soon on all of your favorite game consoles, will bring gamers to which nearby planet?
I don't know. So many fun options. Let's say Venus.
Not Venus, sorry.
No.
Mars.
Yeah.
Yeah.
Figured it was one of the two.
Okay, last but not least, researchers using the Spitzer Space Telescope announced the first direct evidence of debris clouds caused by this type of event.
I can picture this headline and I can't remember exactly what it said. Let's see, debris clouds. I think it was some sort of collision of like, but I can't remember if it was like minor planet collisions, but yeah, I don't know.
I'm gonna give it to you. Collisions around young stars where planets are forming. Yeah.
Okay.
Nice. So I think you got also 3 correct. Nicely done. Tied with Nick there for the lead. All right, Lauren, here's your chance to break away. You've already got 1 correct answer for Astro Advice. So here you go. You ready?
Yeah, let's do it.
Okay. Last week, visionary heliophysicist and namesake to the current solar probe passed away.
It's the Parker Solar Probe, right?
Yep, Eugene
Yeah.
Parker, you got it. This country's recent missions to the moon and Mars are producing exciting scientific results.
Ooh. Is it China?
You got it. Nicely
Okay.
done. Okay. Data released from the Gaia satellite revealed that this space-based object is 2 billion years younger than previously thought.
Ooh.
I give you that. This one's right in your wheelhouse. Data released from the Gaia satellite revealed that this space-based object is 2 billion years younger than previously thought.
Yeah, I'm not sure. I didn't hear about this.
That would be our own Milky Way galaxy.
Oh, cool. That's
Yeah,
neat.
yeah.
It's crazy how little we know about the Milky Way.
Indeed. Okay, number 4. New evidence suggests that NASA lied about having no knowledge of discriminatory practices against members of the LGBT community that calls into question the namesake for which new telescope?
James Webb.
James Webb. They did indeed know what was going on, and they tried to cover it up. Busted, NASA, busted. Okay, number 5. So I think you've already got 3 right, Lauren. So you're already in the lead with 4. So here's a chance to really break away. Okay, last week NASA opened up a 50-year-old time capsule containing what?
Was it samples from the moon?
You got it.
Hey.
All right, so that's a total of 5 points for Lauren. Okay, Danny, so if you want to tie for first place here, you got to get all 5.
Oh man, let's
Ready
set the bar low, please, today.
You ready for this?
Bring it.
Okay, here we go. A new study suggests that this vegetable grown in space might help astronauts maintain good bone health.
Lettuce.
You got it. On Wednesday, this astronaut will return to Earth after setting the new continuous spaceflight record of 355 days.
Mark Vanderhay.
You got it. Russia dismissed reports that these Russian citizens were wearing colors of the Ukrainian flag in support of Ukraine.
Cosmonauts.
Yeah, the Russian cosmonauts.
Yeah.
I'll give you a bonus point if you know their names.
I don't.
All
I
right.
did see the article though.
Okay, 4. This country just launched its most powerful ICBM missile since 2017.
I think China.
Ooh, not China.
Russia.
Nope.
I don't know.
North Korea.
Oh.
Okay, and last but not least, SpaceX just named its new spacecraft to carry astronauts to the ISS after this capsule that was the first to fly an American into space.
Oh no. Do you have any hints?
Well, I mean, I'll give it to you if you just name the first American to fly in space.
So it was a Mercury astronaut.
It was
Wait,
Mercury.
was it technically? Well, so wait. So technically, Wiley.
Yes, technically it was Wiley, but the heralded first American in space on the Mercury spacecraft named the same as SpaceX
Alan
Newcastle.
Shepard.
Alan Shepard, okay.
Okay.
And he flew, oh, now you can already see it. All right, we'll give you 1 point for that one, but not 2.
Oh.
And that makes Lauren our winner with 5 points. Nice work, Lauren.
Thanks. It's gonna be my best week ever. No repeats promised.
Well, you'll be our defending champion in 2 weeks, so we'll see how it goes then. All right, folks, it is time to take a short break, and then we'll be back with our special guest, Steve Lawrence. So go grab some refreshments, do what you need to do, and we'll see you back here in a few minutes. Don't go away. Hello, everybody, and welcome back to the Astro Show. We're here with our special guest, Dr. Steve Lawrence, Professor of Physics and Astronomy at Hofstra University. Steve, thanks so much for joining us.
I'm glad to be here. Thanks.
Yeah, so we'll start off by asking you the question that we ask everybody at the beginning of the guest spot, which is, what's the one question that you wish everyone asks you, but nobody ever does?
Yeah, I gave that a little bit of thought, and I'm going to go for a little bit of sassiness and say I'd like other people to ask me, if I told you you had a heavenly body, would you hold it against me?
Nice. Very nice. That's definitely one for the books. Definitely a little bit different than Jill Tarter's, which was, how big would you like me to write the check to? Well, Steve, tell us a little bit about how you got into astronomy and the path that has led you to where you are today.
Sure. So I grew up in Western Michigan in a very small rural community. And I was always interested in science. And I had the benefit of having a brother who was 4 years older than I was. So I was always trying to keep up with him and read at his level and participate in the things that he was doing. And he was sort of science and engineering minded as well. So my parents enrolled both of us at an astronomy class at the local planetarium in Battle Creek, Michigan. And that involved us actually building a 4-inch Newtonian telescope together. And that was when I was age 11. And so it really sparked an interest that continued. My brother and I were the first members of my family to go to college, and so it was I had a really great opportunities there as a child to foster my interest in science. And so I did my undergraduate work in physics, and while I was in college, Supernova 1987A exploded, and that was in my junior year of college. And so that sort of cemented my decision to go on to grad school in astronomy rather than physics. I was interested in particle physics as well as astronomy, but that sort of event, it was just like, wow, that is really cool. And with the neutrinos detected, it also overlapped with particle physics, so I could keep my toes in both kinds of fields in doing astronomy. So yeah, that was sort of how I got here.
Nice. So we've got this GIF image up that you shared with us earlier. So maybe tell us a little bit about what we're looking at and how that relates to your line of research right now.
All right, so this is Hubble Space Telescope data, and we're looking at about 6 epochs of images taken on a supernova that exploded in 2016. And as scientists discover supernovae in any given year, we letter them. So for this year, 2020, A would be the first supernova discovered early in January, and then B, and then C. And once we work our way through the alphabet once, we then go to 2022 AA, AB, AC, BA, BA, BB, BC. And so this supernova, we've gotten really good at detecting supernova now. So in 2016, this is supernova 2016 ADJ. We've gone through the alphabet multiple times.
Impressive.
And we're even better now. This year, we're probably already well past ADJ. So the images you're looking at they're not direct images. These are actually what we call difference images. I've taken, we had the lucky advantage that the supernova 2016 ADJ went off in the galaxy Centaurus A. And so Hubble Space Telescope had already imaged it extensively. So we had pictures prior to the supernova without the supernova in it. And so I can carefully register and align those images with the new images after the supernova explosion and subtract away anything that is constant and unchanging so that we can just see what's new and what's different from what had been there a few years earlier. And so as you're watching there, the first image in time is the one closest after the supernova exploded, where there's a big dark spot right there in the middle. And then quickly, that's the supernova explosion itself. And over several months, it fades away. And then those rippling rings that you see expanding outwards from the site of the supernova are what we call light echoes. And that is not debris that was ejected from the star, but instead it is light from the star that left the star in a different direction, not headed towards the Earth, but on its way encountered some dust in an interstellar gas cloud, and the dust grains scattered the light in all directions, including some of them got redirected towards the Earth. But since that light took a roundabout direction, a roundabout path to get to the Earth, it shows up later than the actual light of the supernova. And the cool thing about a light echo, one of the cool things about a light echo is that we can use it in a very similar technique that airport radars use. We know when the light left the supernova, we know when the light arrives at the Earth, so we know the total travel distance at the speed of light. And given the angular radius of that ring and the sort of the direction, is it due north, due east, due west of the original site of the supernova, that lets us place the location of the dust in full 3-dimensional precision relative to where the supernova was. And so it's light echoes give us the ability to map dust in 3 dimensions, and that's really a tremendously hard thing to do in astronomy. Getting the distance, the 3rd dimension, perpendicular to the sky is always challenging, but for dust, which generally is very dim and dark and doesn't have any spectral lines, it's particularly challenging to do that.
That is super cool. So why is it important to know these 3-dimensional shapes of dust clouds? How does that help us?
So we're still, there's still a lot of mysteries about what types of stars explode to give us the various varieties of supernovae, and what those stars were doing in the last few years of their life. So a supernova marks the death of a star, but what was it doing in the last 5% of its life just before it exploded? massive stars frequently shed their outer layers, and as that gas expands into space and cools, it forms dust. And so light echoes that happen very close in to the supernova are often hosted by that circumstellar dust. And so mapping the material that the star ejected in 3 dimensions prior to its explosion tells us a lot of information about what may have been going on. Some models hypothesize that one way to trigger a massive star to blow up is to have it absorb an orbital companion. If the orbital companion gets close enough that it's inside the atmosphere of its larger companion, friction will cause the 2 stellar cores to spiral in together and merge. And the predictions are that when that star first starts to enter the larger star's atmosphere, its orbital motion will help it to throw off material, but it will throw it off preferentially in the orbital plane of the 2 stars. And so we wouldn't expect the circumstellar material shed by the stars before they exploded to have a spherical distribution. It'd be more like a flat plane, and the light echoes can help map that out for us.
Very, very cool. I know just a little bit about supernovae through my study in astronomy way back in college, but my mentor who got me into astronomy is Professor Douglas Leonard at UC San Diego, who studies supernovae, and so he definitely is well more versed in this than I am. But for my thesis in my undergrad, I studied a contact binary system in Ursa Major. I don't remember exactly which one yet, but I don't think that one is actually detonated. I think those stars are far enough apart where there isn't enough friction to make their cores combine, as far as I know. But I can't even remember which one it is. So.
Yeah, it would depend if the 2 stars are low enough in mass, they could be a contact binary, but wouldn't necessarily, well, it might take them an extremely long period of time to actually merge. And then when they did merge, it might not be enough to trigger a supernova explosion. You might just end up with an extremely massive white dwarf.
Right. Yeah, I can't even remember what types the stars were. What I do remember, though, is they had an orbital period of only 8 hours. So I was able to get the full period on one night of imaging. It was pretty cool.
Yeah, I have several colleagues who study cataclysmic binaries, and they're all like, it's all I need is one clear night and I can get a paper's worth of data. Studying supernovae, you got to track this, the Hubble data you see there is, it's basically about 2 years of images spaced 3 months apart. So it's, you guys got to really wait. And one reason why I find supernovae so exciting is that they do change in a short period of time. You don't have to wait decades to get some reasonable, interesting changes to these things.
Yeah, you just have to get lucky, right?
So light echoes themselves are cool because I like to put it to people that they allow us to sidestep some of the standard rules that Einstein and other theories have told us. And one of the classic rules that every science buff knows is that it's not possible to travel faster than the speed of light, that the speed of light is the ultimate speed limit in the universe. And yet light echoes kind of let us sidestep that. So looking here in this image, this is an example of more differencing imaging. The first image there are images of the Large Magellanic Cloud, a galaxy that orbits the Milky Way. And in 1987, we saw supernova 1987A explode there. And so pretty much centered in those rings is where the supernova was. And these images then are difference images for an image taken in the year 2000, 13 years after the supernova went off, is subtracted away from later images. And each one of those rings is hosted in a sheet of dust that's between us and the supernova. And as time progresses, the echoes ripple outwards. And so by mapping these over decades, we can develop a really extensive three-dimensional map of the dust. But the cool thing is that those rings are expanding outwards at faster than the speed of light, because there's nothing physical there. We're watching the reflection point of the light scattering off the dust. And if one of those images taken in 2000 and then a later image is taken in 2005, the photons that produced the reflection in 2000 are completely independent and have no relation at all to the photons that reflected off dust that we saw in 2005. So the reflection point is moving through space faster than the speed of light, but the dust isn't, the light isn't. It's just they're uncorrelated events. So there's no violation of relativity, but it does mean that we don't have to wait to scan thousands of cubic light years of volume of space. The light echo sweeps through it incredibly rapidly and gives us a lot of information about a large volume of space in a very short period of time. And then another cool way that light echoes help us sidestep some of the limitations is that since we can't travel faster than the speed of light, it's not practical to imagine looking at any object in space other than from the single sight line that we have from Earth. And so in the image that's on the screen now, those little boxes are highlighting places in the light echo ring from Supernova 1987A where the scientists there at the bottom, Sinnott and al., they used a very large telescope in the Southern Hemisphere to collect spectra of the light echo from those red points. And then we're able to compare those spectra to the spectra we recorded of the supernova itself in 1987. And as this kind of three-dimensional view here shows, the supernova is at the yellow point. The light echoes were sampled at those brown dust clouds, and those dust clouds are scattered in 3 dimensions, giving us a different view of the supernova explosion itself. And so if we advance to the next slide, these are 2 different spectra from 2 different of those light echo clouds. And this is the red tracing and the blue tracing are focusing in on the hydrogen alpha line, emission line from the ejected gas. And we can see that the red tracing is systematically red shifted to longer wavelengths, and the blue tracing is systematically blue shifted. And these are both different from if we trace the spectral profile of what we saw from Earth, it would be more in the middle between those 2. And so the reflection off the dust clouds is letting us look at the supernova from a different angle, from a different perspective than we saw from Earth. And in studying individual supernova, each one individually from its own sightline from Earth, we've noticed that some of them look perfectly symmetric and have no evidence of non-spherical shapes to them, no asymmetries to their expansion patterns, and yet others do. And the question is it some are very nice and symmetric and others are asymmetric, or are they all asymmetric in one way or another? But we just have if they shoot jets out of their north and south poles, but we're looking at them straight above the equator, then it would all be symmetric. And we wouldn't know that from our line of sight from Earth. And so light echoes can help us address those statistics. If you let the light echo expand enough so that you can kind of get a peek around the corner from a different line of sight to the supernova, and they all end up being asymmetric, then we'll know that, well, all supernovae are asymmetric. It's just that sometimes we have an unlucky line of sight from Earth that ends up giving us a false sense of symmetry to them. And then there's a third way that light echoes let us sort of cheat, if we advance the slide. And that's, you can't time travel. As far as we know, you can't time travel. But with a light echo, you actually can time travel to the past. And so what we're seeing here is an image that my collaborator, Rob Feason, and I and others, we used the Hubble Space Telescope to map the Cassiopeia A supernova remnant. And this is a ball of expanding hot gas that we see in the constellation of Cassiopeia. And given the rate of expansion of the gas, we can estimate that the star that exploded blew up sometime in the 1700s or 1800s. But it wasn't recorded. No astronomer in Europe recorded a bright star in Cassiopeia. So that's a bit of a mystery. Was the supernova faint? Was it hidden behind too much dust? Was there just bad weather in Europe for the months that it was bright and visible? And so answering those questions, we need to know what kind of supernova it was, what kind of star exploded. And prior to discovering light echoes from Cassiopeia A, we speculated based on what elemental abundances do we see in the remnant gas, how fast is the gas remnant expanding outwards, what sort of energies and isotopic abundances can we match up to known supernova of stars that we did see explode. But if we advance the slide, there's, so Cass A, and it's a little blurry there, but Cass A, I think, is the supernova that's circled down in the lower right, and several light echoes were detected around it. And so again, we used a large telescope from the ground to collect spectra of the supernova reflecting off the dust now 300 some years later after it exploded. And next slide. In each of these curves, the top curve is the blue curve at the top is the reflected spectrum of Cassiopeia A. And in the top segment, in the top third panel, you see typical spectra of supernova type 1Bs. And in the middle panel, the 5 black spectra below the blue one are the typical supernova spectra of supernova type 1Cs. And then in the bottom panel, you have typical spectra of supernova type 2s. And it's pretty clear that the best match is for the supernova type 2s, and in particular, the ones that are at the top there, the supernova 98J or something like that. So we're able to use the light echo to effectively travel back in time and collect the spectrum of a supernova that took place 200, 300 years ago. So it's fun, it's dynamic.
Yeah, that is super cool. I didn't even know that was possible with supernovae. Any questions from any of the co-stars?
I mean, my first immediate question is, was Cass A bright enough that people should have observed it? Like, was it too dim for them to find, or was it no one was paying attention?
It's a good question, and unfortunately, you get the most information out of a light echo by knowing what the supernova was, how bright it was, what color it was, what its spectrum was like. And so we don't have that information directly. And so it's without knowing the dust, we can't predict how bright the supernova was just from the light echo. So it's the light echo can't help us answer, was it an intrinsically dim event or not? But at least as a supernova type 2, it shouldn't have been particularly dim. Those are generally not as bright as type 1As, but they're generally pretty bright.
Yeah.
And so dust along the line of sight. This is the other nice thing about light echoes, is that our line of sight directly to the supernova might be blocked by too much dust, but the supernova sends light out in 360 degrees in all directions. And so if there are some open holes, we might end up seeing a light echo from a different angle that would then allow us to detect it. And that's particularly, we're overdue for a supernova within our own Milky Way galaxy. And we will know it the day it happens from the neutrino detectors. And so the neutrino detectors will give us a general direction, and big sky surveys like LSST, the Vera Rubin telescope, will probably allow us to either detect the supernova directly very early, but if it's hidden behind dust, we might be able to find it from light echoes that will be propagating out from it. And again, those travel, the light echoes of foreground dust move faster than the speed of light. So we may not have to wait that long, even if we can't see the supernova directly, to see a light echo from it and then get its type and learn more about. The neutrinos are great because they tell us what happened in the core when the star actually collapsed and exploded.
So if you had to hedge your bet, Steve, do you think it's the next supernova? That is, you think it's going to be one of the stars that gets talked about in the news, like Betelgeuse or Antares, or is it going to be some unknown star that just?
Sadly for us here in the Northern Hemisphere, I would lay my money on Eta Carina. In the 1840s, it had a massive outburst and went from being, I forget the exact numbers, but as Eta, the fifth brightest star in the constellation of Carina, it might be in maybe the 50 brightest stars in the sky, but probably less than that. And it got nearly as bright as Sirius for a couple of weeks. But it wasn't a supernova explosion. It just was a massive eruption on the surface of the star. But it's surrounded by all sorts of debris from earlier burps and outbursts like that, as well as with the Hubble Space Telescope, we can see a wonderful nebula formed from the 1840s outburst. And it's a binary system, and whenever the companion is in elliptical orbit, and whenever the companion dives in close, there's all sorts of X-ray activity from the interactions of both of their winds. It's a really violent and it's a system with a lot going on. And so it's from the orbit, we can estimate that it's sort of like a 25 solar mass star. So it doesn't have long to live. Even if had been born recently, it doesn't have long to live. So that's sort of my my expert opinion on if you had to put money down, Eta Carina is the most likely candidate to blow up tomorrow.
Cool. I won't hold my breath, but
I mean, I'm in the southern hemisphere, so fingers crossed.
Well, take some pictures, Nick, if it goes, all right?
So I'm just curious, you were saying that the light echoes can go faster than light because it's based off of where the reflection point is on the dust. So what sets where the reflection point is on the dust, I guess? Is it like the energy of the light? Is it just a pure function of distance from the supernova? Or?
Exactly. So I do have if we can go through my slides until you see there we go. So let's get to the start of this slide. All right, so there's the Earth, step forward one. There's the supernova or nova explosion, and that's the light that we see travels straight to us. So if I've got a dust cloud there, then light has traveled to the dust first and then gotten to us, and it shows up late. And so if we throw in some more dust clouds, and then one more. So, and any one night, so the little blue T is the delay time. So let's say it's been 18 months since the supernova, and I'm seeing light echoes. The only dust that could be giving me a light echo is dust that falls on that ellipsoidal dashed surface. And it's a 3-dimensional ellipsoid, so we need to rotate it about the line that joins the Earth and the supernova. And so it's an ellipse, and the Earth is at one focus of the ellipse, and the supernova is at the other focus of the ellipse. And as time progresses, that ellipse just keeps expanding outwards. So if we go one more, and so the light echo sweeps through any one dust cloud once, and then moves on to more distant dust. And in the speed of the expansion is exactly equal to the speed of light in a vertical plane cutting through the supernova, the plane of the sky at the supernova. The light echo ring would expand at the speed of light. If the dust is behind the supernova, it's actually going slower than the speed of light. If it's straight behind the nova, the far end of the ellipsoid moves away from us at half the speed of light. And then any dust that's in the foreground between us and the supernova, that part of the vertical cut through the ellipsoid there, that ring expands faster than the speed of light, and it does so faster and faster and faster the further out in front of the supernova you get. And so this will be particularly amazing if we have a supernova in our own galaxy, because dust that's halfway between us in that supernova the light echo will be expanding through there at maybe 20, 30, or 40 times the speed of light. And yet the dust will still be close enough to the supernova to get lit up by it. And so we will be able to develop an incredibly exquisite map of interstellar dust between us and that supernova if it happens, on our half of the galaxy, so that it's close enough that it's not the supernova itself isn't dimmed too much by interstellar dust, and then so that dust anywhere along the path between us and the nova is still close enough to the supernova to be lit up by it.
Got it. Thank you.
Hi, Nick here. Big fan of dust. Although typically in emission and absorption. So I'd love to hear a little bit more about the reflection side of things. What size grains we talking about? What do you think the composition is? What are you learning about,
Yeah, so the what we find is that so far most like the dust in the Large Magellanic Cloud is pretty similar to dust in our own galaxy in terms of the grain size distribution and the chemical composition. One of the ways that one of the hooks for my Hubble Space Telescope proposal for the Supernova 2016 ADJ was that it took place in Centaurus A, which is a giant elliptical galaxy, and those usually don't have any dust in them at all, but Centaurus A has this huge, dark, dense, rich dust lane in it that we interpret as having come from a smaller spiral galaxy that the giant elliptical galaxy consumed, that the two of them orbited together and the giant galaxy just shredded the disk galaxy, and the dust from the disk galaxy is now distributed throughout the giant elliptical galaxy. So the idea was, let's use the light echoes to see, can we see, is there a different grain size distribution? Is there a different chemical composition? Because that dust has had a very violent recent history of being shredded out of its normal galaxy, and presumably lots of supernovae and star formation and other shocks and violent things going on as the spiral galaxy was plummeting into the X-ray halo of the giant elliptical galaxy.
Cool.
But yeah, if we have really good spectra of the original supernova, then we can, and particularly if that data extends well into the infrared, then we can get very good limits on the distribution of the grain sizes, and even distinguish between carbon-rich graphene kind of dust and silicate-rich sand-like dust.
Yeah, that's what we're trying to distinguish too, but in the emission end of it.
Yeah.
So it'll be interesting. And I guess I'm just thinking dust, it usually, plays with the wavelength of the light. So so you're Hubble, so you're looking at visible light. So you're probing some down to some, small size of dust that's on order of Hubble wavelengths, right?
Yeah. So it's sort of, from a tenth of a micron up to tens of microns in size for the grain size distribution. If we could go forward to the V838 Mon animated light echo image.
Yeah.
There. So this is cool because in the earlier images, you'll notice that the outermost ring of the echo is very blue, and then the inner parts are more yellowish white, and that's a function of this star is not an exploding supernova. It's more like what Eta Carina did. It's a massive star that just burped up its outer layers and became extremely bright when it was doing it. And the dust that you're seeing there is unrelated. It's in the foreground. It's not related to the star itself. But when the star first erupted, it was much, much, much hotter and bluer. And so the outermost layer of the echo is reflecting that period of the star's color and brightness. And then the rest of it is more on the cooling side of the peak of the light curve of the erupting star, and is more, sort of 5,000 to 4,000 Kelvin photosphere kind of temperature and stuff. Dust tends to scatter blue light better than red light, so the light echoes are always bluer than the original supernova star was in their broadband colors.
Yeah, I was wondering if you'd can you go to shorter wavelengths too? Is anyone looking at light echoes in UV or X-ray?
The trouble with those is that when the original star, like Supernova 1987A, we've tried to get the ultraviolet echo for it several times, and the IUE satellite gave us one good detection, and then
Sounds like a paper. No.
follow up with Hubble failed, and so we don't. And Hubble was much more sensitive, so we don't know if we just got unlucky in that we were targeting places where we knew there was visible light echo, and we just don't know if we got unlucky in that dust wasn't good at scattering ultraviolet light, or there happened to be a lot of dust between the dust and gas between that dust and the supernova, so all of the UV light had already been absorbed and dimmed before it got to this dust, so that it wasn't able to reflect it to us effectively. There are also X-ray light echoes that have been detected around quasars and such. When they have massive outbursts, blazars and quasars, when they make a massive X-ray outburst, you can often see X-ray light echoes coming out of those off of, it's actually dust that's in our galaxy that happens to be just slightly redirecting the X-ray photons, scattering them at a very tiny angle on their way to us. So.
Or grazing incidents and that sort of thing.
Yeah, exactly. Just like the mirrors have to be grazing.
Just like the mirrors, yeah.
The other trouble with ultraviolet light is just that the supernovae themselves, like Supernova 1987A, it's estimated that it was emitting strongly at ultraviolet wavelengths for only a few hours, just when the original supernova shock was just breaking through the atmosphere of the star. So the light pulse there is incredibly narrow in time, and so the light echoes themselves also end up, in a thin sheet of dust, being an incredibly narrow ring without as much signal as you get with the optical dust, because Supernova 87A in particular was extremely bright for like 3 months. So the light echo ellipsoid has a radial thickness to it that helps enhance the thickness and brightness of the light echoes.
Fun stuff. Thanks.
Yeah, it's incredible. I hadn't thought about the light travel time issue with this stuff before, but yeah, it's pretty cool that even though stuff is not moving faster than the speed of light, the reflected signals do, based on where you're seeing them from.
Yeah. The classic analogy is if you had a lighthouse near an infinitely long wall, then if the lighthouse makes one complete turn in 30 seconds, the beam of where the beam from the lighthouse is hitting the wall, that reflection point has to start infinitely off at the left side and go all the way to the right side and get around back to the left side in 30 seconds. And so it has to end up moving faster than the speed of light. But
Right.
the photons themselves aren't doing it. It's just the reflection point off the wall ends up moving faster than the speed of light.
Yeah, it's reminding me of this really cool exhibit at the Exploratorium in San Francisco that I used to go to as a kid. They had this shadow room, and the room, the floor was at an angle. And so when you stood on one side of the room, your shadow was really small. But if you stood on the other side of the room, your shadow was huge, and they'd flash this light to create the shadows. But you could be on one side of the room when one flash of light went off, and be on the other side when the other flash of light went off, and it looked as though you were traveling this huge distance between flashes, but it was like 10 feet. And it was just because of this weird angle in the room. So yeah, very, very fun stuff. We're just about out of time, Steve. Anything that you want to leave us with, either with your research or other stuff about your career in astronomy, or last words of wisdom for our viewers? Anything you'd like?
Yeah, so in addition to studying supernovae and light echoes, one of my passions is issues of diversity and equity and inclusion in astronomy, and particularly as a gay man myself, for those issues as they intersect with gender and gender identity and sexuality. And so if anyone in the audience on the panel is of a queer gender and has an issue that they would like to bring to the attention of the American Astronomical Society, we have a standing committee. The acronym for it is SIGMA, SGMA, that you can, if you search for SGMA, American Astronomical Society SGMA committee, you'll get to our webpage with the contact information for the chair there. I'm a past chair of the committee, and we really want to hear about problems and issues, and through the committee and through our email distribution lists, link people up with resources to help solve those problems. So
that's really awesome. I'm glad to hear about that committee. And yeah, we were so psyched to find the physicists and astronomers out list. We had no idea something like that existed, but are there over 300 names on it now?
Yeah, and it's a mix of course, there's a lot of gay, lesbian, trans astronomers on the out list, but we're very pleased that we have a large number of straight allies who've signed up on the out list as well, so that if there's an undergraduate student or a graduate student who's afraid to come out, they can look at the out list and see, is there a straight ally at least in their department, if not an actual queer astronomer in their department, that they can approach as a mentor and to network with, and to connect with better resources.
That's super cool. Thanks for being a part of that. And yeah, we're just about out of time. So Steve, thank you so much for being here with us tonight. It's been very cool to learn about the stuff you study with light echoes. So thanks so much for your time. Really appreciate it.
No problem at all. I mean, as everyone on the panel can agree, you get us talking about our passion and you can't shut us up. So
we're the same way. We get it. And we've got a thank you gift for you, and Maggie will follow up with you to get that to you. So thanks again. We really appreciate it. Yeah, thanks to all the co-stars for being here as usual. Wouldn't be the same without all of you. And thanks for being brave to step up to the trivia quiz. I know you didn't have time to quiz me today, but I will make sure to give you time to hold my feet to the fire as well on the next Astro Show. So come up with some doozies for me, and I'll let you start with your questions next time. So thanks to all of you for being here. It's a lot of fun. And thanks to all the folks behind the scenes that make the Cosmos Show happen. Maggie, our operations director, Gavin, our screen master, the Wyoming Stargazing Board of Directors, and all of you at home watching. We really appreciate you tuning in, and we hope to hear from you live at some point on an upcoming Astro Show. We'll be We'll be back in a couple weeks. But until then, be well and don't forget to look up. We'll see you next time. Bye.